So let's pick up from where we began. We said we're looking at the link between diffusion and conductivity, and this part of the derivation, we're saying that the change in the concentration is not changing at all. Okay, so the only thing that can happen is an electric field being set up, and so there's movement of the charges according to that electric field. Okay, so in this case, this whole thing reduces down to the down to this here. Okay, so it basically S is equal to negative F of ZF, and then this E has got a line over it, which at least in my notes indicates that it is the electric field, or the potential difference, or the potential across that. So if we've got some sort of, potential here across that, and so that's great. We've got that, and we also know from the mobility that we calculated earlier, which is the speed divided by the electric field. That's what our mobility is, and we have. So we can kind of rearrange this equation using this relationship here to have a description of F. So F in the first case is U divided by ZF. Okay, so this frictional constant, this thing that is the frictional constant. If you just have the electric field, the electromigration, pure electromigration, then this is what the frictional constant is equal to. Now let's think of the second situation when the electric field is 0. So that means that you've only got a diffusion part of this. And so in that case you've got S is equal to this first bit here, which is going to be negative FRT over natural log of A dx. Now if you take the integral of 1 over A, then you're going to get the natural log. So one way of rewriting this so that we get rid of the natural log is using this little trick here, which is you can divide by A, and then it's only dA dx. And so the reason you can do that is because if you integrate this, you would get the natural log from this 1 over A here. So it kind of cancels it out, because this does the derivative, and the integral here would give you the natural log. So it's quite a nice little trick there. Now we also have to note that activity is linked to concentration through this relationship here, and so we can rewrite this as negative F RT over gamma C d gamma C dx. Now the flux is going to be equal to the speed and the concentration. Let me just check that. Yeah, so the flux that occurs is due to the concentration and the speed at which those molecules go. So flux is molecules per second. So that kind of makes sense. So it's molecules concentration per second, and so you times it by the speed. That gives you flux. So we have to use that relationship, that the flux is then going to be equal to the speed times the concentration. And so using that, we can say that so we're putting, this is speed, remember, this is the speed here, so we're putting this into there and we're multiplying it by the concentration. So we have, and actually what that does in the end is it cancels this out with that down there, and so we're left with that the flux that's going, the movement of those molecules is just going to be this frictional constant RT divided by gamma, because the concentration has been cancelled out, and then the change in the concentration as a function of distance. Okay, and I mean ideally you'd expect that that the activity coefficient doesn't change, and so we can take that outside of this derivative, and so that comes here, and we can move that out of there, and then you have the activity coefficients cancelling, and so you end up with negative F RT is just the change in the concentration with distance. So we also know, we've also derived earlier that that the flux, according to Fick's law, is negative d dc dx. And now we can see, look, we've got a relationship between the flux and this concentration gradient in terms of this frictional coefficient, as well as in terms of the diffusion coefficient. And so we can now write that d, if we use that and that relationship, d is equal to this frictional term RT. Great. So basically the diffusion constant is some temperature scaled version of the frictional coefficient. Now we can use the fact that we derived the frictional coefficient earlier in terms of just the mobility of the electric field mobility, and we can put this in here. And so the frictional coefficient calculated earlier, so I'm just going to put U divided by ZF. That's what we calculated from the first bit of the equation. And times by RT. So this is a really nice result. We can relate the conductivity that we can measure right easily with a little multimeter with the diffusion constant, which is much more difficult to measure. So that's really helpful. So we can measure the diffusion constant if we know the conductivity and the mobility of those compounds that we're those ions, and then we can calculate the diffusion constant. So that is great. It's a really good result. And so that's just a derivation of the Nernst-Einstein equation. Hopefully that's helpful.